This next section of our notes is going to be covering colligative properties. A colligative property is defined as a property that depends on the amount of solute particles that are present, but not on the identity of those particles. So what that means is that it doesn't matter what type of substance we dissolve into the solvent, the amount of the solute particles that are present will affect the properties of that solvent. During this lesson, you should be able to distinguish between strong and weak electrolytes, list the 3 colligative properties and explain why they are classified as colligative properties, calculate freezing point depression, boiling point elevation, and solution molality of non-electrolyte solutions. Calculate the expected change in freezing point and boiling points of an electrolyte solution, and discuss causes of the differences between expected and experimentally observed colligative properties of electrolyte solutions. An electrolyte is a substance that, when dissolved in water, has the ability to conduct an electrical current. You can see from the pictures below that when we place certain types of compounds into water and dissolve them, you can get the electricity to flow through and the light bulb to light up. We have 3 different classifications for electrolytes. A strong electrolyte is a substance that will dissociate completely when dissolved in water. This will include all ionic compounds and strong acids and bases. When you have a strong electrolyte and you get that complete dissociation, you can see here in the picture as the ions begin to separate, you have a sodium ion as the gray, you have the chlorine ion as the green. They are surrounded by the water molecules. We talked about that process of dissociation in class 2 weeks ago, where you'll have the water molecules separate the ions from each other, and as those ions are able to move through the solution freely because they're now in the liquid state or an aqueous state, they're able to conduct electricity and carry the electrical current through the water solution. We have a weak electrolyte, which is a substance that will only partially dissociate when it's dissolved in water. Typically, you have polar compounds, such as weak acids and bases. With your weak acids and your weak bases for your weak electrolytes, you can see here's a molecule of hydrofluoric acid, HF. You only have a few of the molecules that will actually dissociate. The vast majority of them will stay in their molecular form. So you can see here in the picture, you have the HF molecule, a little bit easier to see it on this one over here. There is a small little hydrogen off to the side here, and then when it separates out, you'll get an H3O plus ion and an F minus ion that will form as a result. But again, the majority of the molecules will stay together as the HF molecule in solution. Typically with your weak electrolytes, less than 5% of them will actually dissociate. And then finally, we have a non-electrolyte, which is going to be a substance that does not dissolve, or does not dissociate in water, and therefore will not conduct an electrical current. Typically, these are going to be your covalent compounds, such as sugars or alcohols. We're going to take a moment to discuss the differences between your strong and your weak electrolytes. When you have a strong electrolyte, it will dissociate completely when it's dissolved in water. So when we look at these types of reactions, they will go to what we call completion, where all of the reactant molecules will completely dissociate to form the products. So you can see in this first equation the hydrochloric acid HCl, then notice the arrow going in one direction producing H plus and Cl minus ions. This tells you, because it has only one direction for the arrow, that it is a strong electrolyte, whereas if you look at the second example here with a weak electrolyte, which is vinegar, acetic acid, it only partially dissociates. So once again, that means only a small portion of the parent molecules will actually break up to form the products. So in solution, you have a large percentage of that parent molecule still intact. We represent this equilibrium system by showing it as a set of double arrows, one pointing in each direction. This tells you that there are just as many of the product molecules reacting together to reform the parent reactants as there are the parent reactant molecules breaking down to form the products. I just want to take one last moment to review the electrolyte versus the non-electrolytes. For your ionic compounds, all of them will be classified as strong electrolytes, regardless of whether or not they are soluble or insoluble. This one is always very tricky for students, especially at the very beginning, but just understand that even if we have an insoluble compound, something that does not dissolve well in water, there is still that small portion of it that does dissolve. All of those ions will completely dissociate for the part that does dissolve. So as an example for something like that, if you look at the formation of silver chloride, it is a solid. When it reacts, it will form a white precipitate. However, there is a small portion, which we will show as that double arrow again to represent an equilibrium system. There is a small portion that will dissolve, and that small portion will break down into aqueous ions of both silver and chloride. And so because it does completely dissociate for the part that does dissolve, there are no silver chloride molecules that are aqueous in solution, we classify them as a strong electrolyte. Your strong acids as well will completely dissociate or ionize. We'll talk about the ionization concept a little bit later, but they will completely dissociate or ionize and therefore are listed as strong acids and strong electrolytes. Your strong bases are ionic compounds because we're talking about group 1 and group 2 metal hydroxides. So they would fall under the umbrella of that first category. When we talk about your weak acids and your weak bases, those are the only compounds that are going to form weak electrolytes. No ionic compounds will do that. With your weak bases, typically they're going to have some type of amine group that's attached to them. So for those weak bases, typically you're going to find it as an NH2 group that's attached onto some type of hydrocarbon. So it's very closely related to ammonia. They're just replacing one of the hydrogens off of the ammonia with some type of hydrocarbon. So an example for something like that would be a compound that we call methylamine, which is CH3NH2. The NH2 part there signifies that it is a weak base. And then for your other molecular compounds, anything that is not a weak acid or a weak base will be classified as a non-electrolyte. So something like sugar, as we said, alcohols, many other different types will be classified as those non-electrolytes. So once again, the strong electrolytes will conduct a current very well. The weak electrolytes will partially conduct a current, so you'll get some current that goes through, but not a lot. And then the weak electrolytes, there will be no conduction taking place. In order to understand the concept of colligative properties, we must first look at the effect of adding a solute to the vapor pressure of the solvent. You will recall from our work with gas laws that as a liquid begins to evaporate, it will reach an equilibrium with the gaseous phase for its particles as they are able to escape the surface of the liquid. As the temperature increased, the amount of vapor particles that had the energy to escape the liquid would also increase. When we look at the pure solvent, which would be the picture on the left, you'll notice that there's a larger proportion of gaseous water molecules that are over the liquid than when we have the solute added to the solution. When we look at the picture on the right, what you will notice is that there's essentially a blocking effect of the larger solute molecules at the surface, which is preventing a larger amount of the water molecules to escape the surface, therefore having a smaller number of particles of the gaseous water vapor above the liquid for that solution. As a result of that vapor pressure being less, it is going to affect the properties of melting and boiling points as well as osmotic pressure. The first of our colligative properties that we're going to look at is freezing point depression. As the name suggests, when we have a solution, the freezing point of that solvent is going to decrease as the additional solute particles are added to that. In order to illustrate this, we're going to look at the phase diagram for, in this case, water. When we look at our typical phase diagram, remember the line that's going vertically here represents the difference between the solid and the liquid state. So at any temperature and pressure along this line, that would be considered its melting point. So you can see by adding the solute and lowering the amount of vapor pressure that the liquid has, the blue line represents the solution, whereas the dark red line here is representing the pure solvent. So when we look at this, you'll notice that the freezing point is being pushed back to the left here, which means that we are lowering the temperature at which the melting and freezing will occur. This is why we add salt to the roads when it's wintertime and we have ice on them, because typically the freezing point will lower enough where the outside air temperature will be high enough to actually melt the ice off the road. Using the same diagram, we're now going to describe boiling point elevation. You'll recall that the definition of boiling point is when the atmospheric pressure is equal to the equilibrium vapor pressure. So when we lower the vapor pressure by adding a solute particle to it, that means that we're going to have to supply more energy to vaporize more of the solvent molecules to create the necessary equilibrium vapor pressure. And so as you can see here, we have 1 atmosphere of pressure. You can see that the temperature curve is shifting to the right, which means that we now have to have a larger temperature in order to produce the same amount of vapor particles for the solution. So therefore, the temperature of the boiling temperature for that liquid will increase. So we're now going to look at the way that we can determine what the new boiling point or freezing point for the solution will be. Because that colligative property depends on the number of solute particles that are present, the change in temperature is going to be directly proportional to the molality of the solution, using what we call the Van't Hoff factor. The Van't Hoff factor is the number of particles a substance becomes when it dissolves. So the importance of this is where we're talking about those electrolytes versus non-electrolytes. If we look at something like sugar, C12H22O11, when we place that into water and dissolve it, it is going to stay together as a sugar molecule. It just simply dissolves and becomes aqueous. So I have a 1-to-1 ratio. This Van't Hoff factor, which is the I in the equation, this is describing the number of particles. So when I look at something like sodium chloride, when we take the solid sodium chloride and we place it into water, I would then get a particle of Na plus and a second particle of Cl minus. So I have effectively doubled the concentration of solute particles, because if I started with 1 mole of the NaCl, I'd have 1 mole of the sodium ions plus 1 mole of the chloride ions. So the total number of moles of particles in solution would now be 1 plus 1, or 2 for the particles. So I would use the 2 as my value for I. Now, as far as our solution's equation here, the TB for the solution, think about that as your final temperature, and the TB for the solvent as your initial temperature. You'll always be given the value for the initial temperature for the solvent. We have the I again, that Van Hoff factor, the KB or the KF, that is your mole-al freezing or boiling point constants. Those will always be provided to you in the problem. And then finally, the little m, that is your molality for the solution. So remember, molality, moles of solute divided by kilograms of your solvent. So you see here down at the bottom a number of different solvents with their normal boiling points, their KB, their normal freezing points, and their KF. Keep this chart handy because we're going to be looking at it for multiple problems. So the way how you would look at this, when we see this KB value for water, that is telling you that for every 1 mole solution, you'll have an increase in the boiling point of 0.51 degrees Celsius. So for instance, if we had that 2 mole solution for the sodium chloride that we were talking about above, instead of having a boiling temperature of 100, it would be 100 plus 2 times the 0.51, which would represent a 101.2 degree boiling point. When we look at the normal freezing point, remember the freezing point is being depressed. That's why it has the negative sign out in front. If you want, you can put a negative on all these values just to begin with so that you don't forget, but because the temperature is dropping, that means that my final temperature will always be lower than my initial temperature. So my change in temperature will always be a negative value. So we're now going to do a quick little concept check. Pause the video for a moment and try to answer this question. Which aqueous solution will have the lowest freezing point? So in order to solve this problem, what we want to do first off is identify whether my substances are going to be a strong electrolyte, a weak electrolyte, or a non-electrolyte. So just to review that, if I have a strong electrolyte, that is going to be an ionic compound or a strong acid. If I have a weak electrolyte, that is going to be a weak acid or a weak base. And if I have a non-electrolyte, it is going to be a covalent compound. So when I look at my first one, I have CaCl2. That is an ionic compound, so therefore it's going to be a strong electrolyte, and it will completely dissociate. So I would have 1 calcium ion and 2 chloride ions that would be produced. So if I start with a 0.050 mole solution, sorry, that should be a little m, then I will get a 0.05 mole solution of the calcium ions, and I have 2 times a 0.05 mole solution of the chloride ions, or 0.10. So my total, I can then just simply take and add my 2 molalities together, and so for the calcium chloride, I'd have a total of 0.15 mole for that solution. When I come to my next one, for B, sodium chloride, NaCl, once again is also an ionic compound, so it will split into Na plus and Cl minus ions. Since the initial molality is 0.15 mole, that will give me 0.15 mole for each of the sodium and the chloride ions, so I would have a total of 0.30 mole for that solution. When I look at C and I have HCl, That is now an acid. It is a strong acid. So again, these strong acids that you need to watch out for, you have HCl, HBr, HI, HNO3, HClO4, and H2SO4. If it's not one of these 6 acids, it would be classified as a weak acid. So for this one, I would have a single arrow to represent the fact that it is a strong acid. So it's going to form H plus and Cl minus. So if I start with a 0.10 molal solution, I would have 0.10 molal for each of those. So I would have a total of 0.20 molal. When I come down to the last remaining ones, over here we have that partial ionization that occurs, but again we're talking about less than 5% that will actually dissociate. So the vast majority stays in the molecular form. So I'd have H plus and I'd have the CH3COO minus, that acetate ion. But again, we would treat it as if it is a single molecule, since only that small percentage would dissociate. So it would stay as 0.05 molar. And then finally for E, I have 0.20 molal. Notice this one here, that is a covalent compound, so it will not dissociate, it will just simply dissolve, so it would stay as 0.20 molal. So when I'm looking at all of these, the one with the greatest molality for all of the different ions or particles in solution would be the sodium chloride, NaCl. So let's look at our first example problem of how to calculate the freezing point or boiling point of a solution. So example 1 says, referring to table 13.3, calculate the freezing point of a solution containing 0.6 kilograms of chloroform CHCl3 and 42.0 grams of eucalyptol C10H18O, a fragrant substance found in the leaves of eucalyptus trees. So you'll notice from our chart, we can come down here and we find our solvent, chloroform, CHCl3, and it tells you that it has a normal freezing point of negative 63.5 degrees Celsius, and it has a Kf value of 4.68. So the first thing that we need to do, since I'm given grams of the solute, is I need to convert that into moles to calculate its molality overall. So I'll start 42.0 grams C10H18O, and we would find from our periodic table that the molar mass for the C10H18O is 154.28 grams. So that will give me a total of 0.272 moles. And then we can divide that by the 0.6 kilograms, again for the molality formula, moles per kilogram. And that gives us a molality of the solution equal to 0.454 molal. I can now take that and plug that into our equation. So we can take our equation, delta TF equals a negative Kf times M times I. In this case, C10H18O, that is a covalent compound, so we know that my I will be equal to 1 because it's a non-electrolyte. So when I start off this process to solve for the delta TF, what I want to do is take the negative of the 4.68, and that's degrees C per molal, and we're going to multiply that times the molality of the solution, 0.454, and that equals negative 2.12 degrees Celsius. So now to solve for this, knowing that the delta T is equal to negative 2.12, we can set that equal to the TF minus the TI, and the TI again is the negative 63.5 degrees Celsius. So I have TF minus 63.5 equals negative 2.12. So the TF will be, in this case, negative 65.6 degrees Celsius. So for our last colligative property, osmotic pressure, I'm going to begin by telling you the last of my blonde jokes for this unit. The blonde joke is, why did the blonde climb over the chain link fence? To see what was on the other side. When we talk about osmosis, we have a semi-permeable membrane that allows the passage of some particles while blocking the passage of others. So if you think about that chain link fence, you have the wiring that is set up in the diamond-shaped patterns that allows you to see directly through the fence. When we talk about that fence, that is essentially our semi-permeable membrane. If I throw a large object at the fence, such as a baseball or a softball, the holes in the fence are too small to allow the passage of the baseball or the softball to go through it. However, if I took something like a penny or a quarter and I threw it at the fence, then we have the ability of that penny or quarter to pass through it because it is small enough compared to the holes. So when you look at your solvent molecules, the passage of the solvent molecules from one side of the membrane to another, you essentially have these particles for the solvent that are small enough to pass through the membrane while the solute particles are too large. So the solute particles would be your baseball or your softball. Now, as the solute concentration increases, what you'll find is that you have more of the solute particles that are pressed right up against that semi-permeable membrane and make it so there's smaller amount of spaces or volume for the solvent molecules to be able to pass through that membrane. As you have a lower concentration and there's not as many solute particles, that can be illustrated with the second example. I know the concentration is still the same, but the particles are further away, so that can illustrate it by the fact that you have a smaller number of particles. You have less particles that are pressed right up against the side of the membrane, and so it more freely allows the transmission of the solvent from one side of the membrane to the other. As far as the process of osmosis is concerned, that is the movement of the solvent molecules through a semi-permeable membrane, and this is going to go from the side of the lowest solute concentration to the side of the higher solute concentration. When we talk about the osmotic pressure itself, the osmotic pressure is the amount of pressure that must be applied to stop that process of osmosis. For us, there is an equation that we could use to solve for osmotic pressure and relate it to our gas laws. However, it is not something we're going to cover in this unit. So all you need to know about osmotic pressure is what osmosis is and the definition of the osmotic pressure being the external pressure applied to stop the osmosis. From here on out in our presentation, we're simply going to be working practice problems. This first problem is a freezing point depression problem. It says, what is the freezing point depression of water in a solution of 17.1 grams of sucrose, C12H22O11, and 200 grams of water? What is the actual freezing point of the solution? So just a couple of things that I want you to remember. Because the freezing point is being depressed, the solution should always have a freezing point that is lower than just the pure solvent. The other thing that you need to be able to do is, number one, identify what is your solute versus what is your solvent. Most of the time, remember, the amount of grams will be less for the solute than for the solvent, but not always, so you have to be careful. So watch for keywords like dissolved or in the solution, because that'll tell you what is your solute and what is your solvent. The second thing that you need to focus on is what type of solute you have. In this example, since we have sucrose, C12H22O11, that is not a weak acid, but you will notice that it is a covalent compound, all nonmetals. So therefore I have a non-electrolyte for the solute, which means in this case that the I would be 1. Off of your table that I was referencing earlier, that table 13.3, we have a few different things that we need to be watching out for. Number one, the freezing point for water is equal to 0 degrees Celsius, and the Kf value for the molal freezing point constant for water was 1.86 degrees C per molal. So when I look at this, what I need to start off with is to calculate the molality for the sucrose solution. So I'm going to determine the number of moles by taking the 17.1 grams of the sucrose and dividing that by its molar mass, which is 342.34 grams. When we plug that in and we solve, we end up with 0.050 molal, and we have 200 grams of water, so if we divide that by 1,000, that would give us 0.200 kilograms of solvent. So if I take 0.05, divide it by 0.2, that gives me 0.205 for the molal. So I have enough information to plug in and solve for delta TF. Remember, that's our change in the freezing temperature. So I take the negative because it is going to drop the temperature. So I take the negative of 1.86 degrees C per molal, and then I'm going to multiply that times the 0.250 molal for the solution, and we get a temperature change equivalent to negative 0.465 degrees Celsius. So to solve for the final temperature of the solution, it's a little redundant when water is the solvent since 0 is the initial temperature, but just for practice, I would take the negative 0.465 degrees, I would take my TF minus my TI, and again that TI is 0 degrees Celsius, so I'd have negative 0.465 plus 0 equals TF, so my TF and my change in the freezing point will both be the same at negative 0.465 degrees Celsius. Next, we're going to look at the boiling point elevation for a non-electrolyte solute being dissolved in 400 grams of water. We have enough information to solve the problem because it tells us what the molar mass is, even though we don't know its identity. So remember the boiling point elevation. The boiling point is going to be higher than what the boiling point would be for the pure solvent. So off of our chart, a couple pieces of information that we need. The boiling point of water, 100 degrees Celsius, and the molal boiling point constant, the Kb, is equal to 0.51 degrees C per molal. And once again, because we have a non-electrolyte, the I value will be 1 for this as well. So initially, the first thing we need to do once more is to calculate the molality for our non-electrolyte solution. So I'm going to take the 20.1 grams and we're going to divide that by the 62 grams per mole. When we divide that out, we end up getting 0.324 moles, and then we're going to divide that by the 0.400 kilograms of the water, and that gives us a molality of 0.810 molal. So now from there, we can plug that into our formula. Delta TB equals the Kb, notice it's a positive value this time, times M times I. So I have the 0.51 degrees Celsius per molal, multiplying that times 0.810 molal, and multiplying that times 1 for the value of I. So my change in the boiling temperature for this particular example will be 0.413 degrees Celsius. So my new boiling temperature, if it were asking us to solve for that, we would take the 100 degrees, we would add it to the 0.413, and we'd have 100.413 for the value. For significant figures, remember that the boiling point is an exact number, so it would have an unlimited number of significant figures. So my final answer would be predicated off of how many digits my change in the boiling temperature would be. Our next problem is what is the expected change in the freezing point of water in a solution of 62.5 grams of barium nitrate, BaNO3(2), in 1 kilogram of water. So once more, the key thing that we need to focus on to begin with is what type of solute do we have? Barium nitrate, metal polyatomic ion. This is an ionic compound, so therefore it is going to dissociate. So we need to see how many ions would dissociate into the solution. So I'd have 1 barium ion and I would have 2 nitrate ions. The easy thing to do is just add up the subscripts. I have 1 for barium plus 2 for the nitrates, not the 3, but just the 2 because the NO3 acts as a single unit. So I have 1 plus 2 for a total of 3. So I know that my molality will effectively triple from what we calculate. So I'm going to calculate the initial molality by taking the 62.5 grams of the barium nitrate, 1 mole of the barium nitrate will be 261.35 grams. So my number of moles will be 0.239. And if I take that amount and divide it by the 1 kilogram of water, that gives us a molality of 0.239. We're still using water, so the change in the freezing point will be equal to a negative of 1.86 degrees C per molal times 0.239 molal, but this time our I is equal to 3 because I have the 3 ions, 1 barium and 2 nitrate ions. So I can multiply those together and I get a change in the freezing temperature of negative 1.33 degrees C. For our next problem, we're going to ramp up the difficulty level just a little bit, and we're going to use some of our concepts of concentrations that we learned last week. So for this problem, we have an automotive antifreeze contains ethylene glycol, CH2OH, CH2OH, a non-volatile non-electrolyte. Remember that term non-volatile simply means that it does not readily evaporate. So we're going to calculate the boiling point and the freezing point of a 25% by mass solution of ethylene glycol in water if the solution totals 1 kilogram. So please remember from our percent by mass that the mass of the solution is equal to the mass of the solute plus the mass of the solvent. So if I have a 25% by mass solution, that means that for a 1 kilogram solution, I would have 250 grams of the solute and I would have 750 grams of the solvent. That would equal 1 kilogram for the solution. So for this problem, I need to begin by taking the 250 grams of the ethylene glycol. So if we simplify the formula, I'd have C2H6O2, and I need to convert that into moles. So 1 mole of C2H6O2 is going to be 62.08 grams. So this would equal 4.02 moles. I can then take this and divide it by my number of kilograms for the water, which 750 divided by 1,000 would give me 0.750 kilograms. So my molality for the solution would be 5.37 molal. So we have two problems. They want us to solve for the freezing point and for the boiling point. So if we start off with the boiling point, I would take my value for the KB, 0.51 degrees C per molal. Again, that KB is off the chart, table 13.3. I'm going to multiply that times the molality of my solution, 5.37, and that change in temperature would be a positive 2.70 degrees C. So now, to solve for the new boiling point, I take 100 plus the 2.07, so I'd have 102.7 degrees C. Sorry, this should just be 2.7. Okay, so now to solve for the new freezing temperature, I take a negative of the 1.86 degrees C per molal, multiply that times the 5.37, and when we do that, we end up with a change in temperature of negative 9.99 degrees C. So I take again 0 degrees minus the 9.99, and that is going to equal a negative 9.99 degrees C. Okay, so our last problem, we're going to determine the molar mass of an unknown compound for our solute. So I have a solution of an unknown non-volatile non-electrolyte was prepared by dissolving 0.250 grams of the substance in 40 grams of carbon tetrachloride. The boiling point of the resulting solution was 0.357 degrees Celsius higher than that of the pure solvent. Calculate the molar mass of the solute. So once again, because I have a non-electrolyte, I know that my I in this case will be equal to 1. So now, knowing that I have my change in the boiling point, which was 0.357, that's now going to be equal to the KB times the M times the I. So, knowing that we have carbon tetrachloride, CCl4, I can look up its molal boiling point constant, which is 5.02. So I can take that information and solve for M. So if I have the 0.357 degrees C equals 5.02 times M, and again the I value was 1, I can take the 0.357, divide it by 5.02, and I get a molality that will be equal to 0.0711 molal. Now, we can then take the molality of our solution, 0.0711 molal, and set that equal to the number of moles, which we'll define as X, over the 40 grams converted to kilograms. I would have 0.040 kilograms of the solution. So to solve for X, I'd multiply both sides by the 0.040 kilograms, and I get my value for X to equal 2.84 times 10 to the minus third moles. So the last part that we need to do to solve for the molar mass is use our original moles formula. So I'd have my moles equaling the mass divided by the molar mass. So in this particular instance, I have my number of moles, 2.84 times 10 to the minus third. I have the original number of grams, 0.250 grams, and I now will solve for X. So with this here, I can take the 0.250 grams, divide it by 2.84 times 10 to the minus third, and that will equal 88.0 grams per mole. So final answer, 88 grams per mole. Okay, so at this point, you should be able to identify what the three colligative properties are and how the change in the concentration will affect those properties. Remember that the identity of the solute particles is not important other than to determine whether or not you have to multiply it by the number of ions. You have some practice problems and a couple little paper lab activity to complete this week. This pretty much wraps up the solutions unit for us. So I'll be online for you guys on Thursday. I think I'm going to try to do it with Teams this time instead of the Schoology. So please try to make the effort to come over at 10 o'clock and ask some questions. Thank you very much for working through this PowerPoint. I will hopefully see you soon.